is we're going to have to pick up some more terminology on about computers. That while you're to be well versed in PLCs, this will impress a lot of people. Plus, now you can converse with people that really understand these things. So, programmable controllers. This is actually chapter 1. So we'll come back and hopefully by the time we get here, we should be able to lecture. I think the first test is scheduled for Thursday when we get back, but I would like to try to get ready to do some labs and get y'all started up. Of course, one lab you have the ability to do now is lab 3-1, and like I said, I've put this on Blackboard, so you don't have to, go through and do a lot of changing. You also can download, or if you got 2 computers, you could also bring up that powers an ASCII code chart that's available up there. I'll give you a copy when you get on campus, but you'll probably need it to do that lab. So chapter 1 just deals with computers. A lot of it says programmable controller overview, but this deals a lot with the terminology or the language we use when we get into these computers, whether this be your laptop or whether it be your tablet or your cell phone. These are all computers now. And so there'll be a lot of things that will start making sense of the way they are, just like Unicode. So now when you tap that emoji, it's sending a code to that other computer. That other computer receives that code, and then it looks up in a chart. Looks up at a chart and pulls the icon, the emojicon up there. See, I don't know how that works now. Describe the invention and development history of programmable controllers. Discuss the benefits of PLCs over electromechanical relay logic systems. So doing logic, we'll learn and we'll actually look relay logic. But basically we have 5 operations that we can do with logic. We can do AND, we can do OR, we can do NAND, we can do NOR, and we can do a NOT. And that's the 5 basic logic functions. Originally we start, and once we can do this logic, then we can set up systems that go into automation. So we'll look at these in detail on how we can take devices and do ANDs, ORs, NANDs, ORs, NANDs, NORs, and NOTs. If you take motor controls, you'll literally wire these up. AND logic, OR logic, NAND, and NOR, and we'll look at those. We'll start off by doing inputs, wiring inputs in ANDs, ORs, NANDs, NORs, and NOTs. And then if you take PLC 2, IoT 196, and Miniterm 2, we'll actually look where we can do ANDs and ORs and NANDs and NOTs on 16 or 32 bit numbers. The PLC that we have, it only goes up to 32 bits. The newer PLCs goes up to 64 bits, which is well above anything that any company would have to deal with. So discuss different types of Intel and Motorola microprocessors. Not really. We'll look at I've got the mask for an i7 processor in here that you can get them yourself. This would be the actual thing that they use to etch the processor into the silicon wafer. The different types of RAM, the different types of ROM, we'll look at that, and this will start making some sense, even maybe on some things that you heard. We'll look at what we call an address decoder. It's kind of hard, easy for us to understand when we actually get into addressing. We'll talk about power supplies, and then we'll look at some Allen-Bradley programmable logic devices. So first of all, we need the term discrete, binary. I've never seen a programming language call it that. Most of the new ones call it bool. So if you see bool, the algebra that we use to reduce, we have an algebra that we use in digital where we can take very long circuits, and we'll in digital you'll look at a little bit how you can create an equation for a circuit using something called Boolean algebra, and then you reduce it using a lot of the techniques that you'll learn in regular elementary algebra to reduce equations. But what's so neat here, you're literally reducing the size of a circuit or a program, which really comes into place. The book calls it discrete, binary, or input ports. Most of your new PLCs call this bool for Boolean, because and if you see this means this is discrete or ones and zeros. Well, some of your PLCs, and this is even becoming popular on your old ones. We live in an analog world, so digital we change in steps, and most of the time it's just 1 or 0, off or on, true, false, and we'll use those terms a lot, true and false. Analog, but we live in an analog world. Temperature does not vary. It's not, if they say the high today is supposed to be 53, it don't go from the low to the high in no degrees. It don't jump, Temperature, sunlight, all this other kind of stuff that we have varies, continuously varies, and this would be analog. Some analog ports are optional, and we'll talk a little bit about A to D and A to D converters. The PLC that we're going to be dealing with this semester has 2 analog inputs on it, and we'll look a little bit on those. It doesn't have any analog outputs, but it's got analog inputs. The Siemens PLCs that we'll deal with, if you take ILT 212, which is PLCs and automated systems, it has 1 analog output port, and it has 2 analog input ports. So we'll talk a little bit about that, and we'll deal with that, the analog portion of the PLC in PLC 2. So basically, analog means something that is constantly varying. And of course, temperature is constantly varying, light is constantly varying. So we live in an analog world. But analog is real hard to transmit and receive. It would take, basically analog would have an infinite number. So time, we count times in seconds. But when we get into digital, we start dealing with milliseconds, microseconds, nanoseconds. Well, basically, in true life, there is an infinite amount of time between seconds, increments of time, excuse me. So analog, we can deal with infinity. Digital, we can't. It's just that digital, to represent large analog quantities, would take thousands of bits. So we got to set a resolution, and we'll like I said, in PLC 2, we'll talk about a little more about the analog inputs and how it actually works. But it runs from what we call an analog to digital converter, which converts it into a binary number with a weight that represents the weight of the analog input. And then we have what we call digital analog converters, which would take a binary number and convert it into a voltage or a current that represents that way. But if I'm dealing with ones and zeros, it's real easy to represent. We can represent them with voltages. We can represent them with currents. Can't represent resistance, guys, because resistance we can't send, but we can send a current and we can send a voltage. So very easy to represent. So when we save these ones and zeros inside our computer, they're saved as voltage levels, where one voltage level would be a 1 and another voltage level would be a 0. And we can store those real easy in very simple circuits. We can transmit it over long distances. Over here, the voltage level would be very important. Over here, all we got to do is make sure we meet a minimum value. If we meet a minimum value for a 1, then anything above that would be okay. When you get into digital, you'll learn about those minimum and maximum values that we deal with in digital. But this is basically a block diagram of a PLC. We have used to the CPU was the central process. It was actually the processor. It was the electronic circuits that does that. In CPUs, we call the whole processing unit. We call it the CPU. Even though the microprocessor is just a little section of that, we call it the CPU. So they identify, one of the things they identify the model is by, we'll have a series of PLCs, like the SLC 500 series, and then we have what we call an LSC 504. So this would identify the actual processor that's inside that and the features that we have. Of course, we have to have a power supply, and these are going to be DC power supplies. Some of the power supplies are actually built into the PLC. The power supply, of course, the power supply is going to take Alabama Power, which is generating AC, and then it's going to convert that over to direct current for our electronics. And that's one of the big advantages of DC is we can electronically control it. The 1100 that we have has a built-in power supply, so it plugs into TVA here at the college, and then we have two outputs where we can get DC out. Now, unfortunately, it's a low, so this is the, let me switch over to my camera. I lost my toothpick. Hold on. So this is the Micrologic 1100, and you can still buy these. And so here's the AC power cord coming in, and it's got two arrows pointing in right here, AC in, L1, L2. L1 would be the black wire, and then L2 would be the white wire, and then green wire, this would be the ground. Then up here at the top, if it'll zoom in, if it'll focus, excuse me. So it's got DC out if it focuses. Let's see if it's going to focus. Yeah, DC out, plus 24, minus 24. You see we're not using that. There's nothing connected up here. We're using the power supply that's inside the actual thing this is mounted on. We call it an Edu-Trainer. This is made by Allen Bradley. So this is a 24-volt supply. By the way, Germany uses red for plus and uses blue for minus. So Siemens is a German company. So that's what you got to get used to. Over here we use black for minus and we use red for that. So anytime you see the blue and the red, odds are it's made over in Europe. So this is the power supply that we're using for our PLC because it's got to run all these outputs over here. And this little power supply up here can't do that. It could probably run these inputs because they don't require any power, but these guys right here would. So this guy has an internal power supply. Some of them don't. The compact logics that we deal with in PLC2 or ILT 196, you have to have an external power supply. It doesn't have a DC power supply built into it, so we have to provide that. All these Siemens PLCs that we have over here, these 314s, that's what this is right there. That's the actual DC power supply. So down here, this is TVA coming in here, or Alabama Power where we're at, and then up here, this would be the output. So these PLCs require an external power supply. So these are Siemens 314s, 300 series 314s. The 14 would specify the CPU, so you could actually look up if you did enough research and actually find what CPU. But basically, that's transparent, or processor it's using. But that's transparent to you. I mean, that's transparent to you anyway. So then we have the actual CPU, and then we have our output modules, our binary output modules. So when the book uses discrete, these are binary, or digital, or bool, which is most of your PLCs call them. And then we would come up here, and then we would hook our output devices up here. Let's just do a light bulb. And then we have this is input rich, duh. So this would be either a sensor, or it would be maybe a push button. Down here, this is where your relays would connect to, your solenoids would connect to, and then some of them have an input-output module. I've seen this a little bit. We do when we deal with some things, and then of course analog. It might have analog or it might not have analog. And that's something that you look at when you purchase the PLC. If it's a rack-mounted modular PLC, then you would buy an analog module, and we'll look at that in a minute. So we have basically used to, when the book came out, we had two definite categories. We have what we call a fixed PLC. If all the units are in one fixed enclosure, the number of input ports cannot be expanded. The number of output ports cannot be expanded. So basically with fixed PLCs, you get what you pay for. So it's very, very important but they're the cheapest. So the fixed PLCs are the cheapest, but you get what you pay for. So it's like when you go out and buy a tablet. Odds are when you buy a tablet computer, you can't, or a laptop computer, it's almost not, you buy what you most of the time now, in the old days like my Lenovo here, I could add more memory to it. And I could change and put another hard drive into it, a bigger capacity. Some of your laptop computers are expandable. Desktop computers, these are very expandable. It's up to you what you buy, and they're very easy to upgrade, to add more memory or add another processor. So this is one advantage of these desktop computers that's starting to move back in. That was becoming obsolete with these laptops, but we realized that these desktop computers had so much more processing power because we could spread them out and cool them down and not worry about a lot of heat and cram everything in a small amount of space. So if you really, really, really want a beefed up computer that can really process some information, then you want to go to a desktop computer. If you want for convenience and portability, of course, laptops, I have to carry mine around all over the place. So I have a couple laptop computers that I have available to it. But fixed PLC. So this is the MicroLogic 1000. But luckily the class is small enough where we don't have to use this guy. This is a fixed PLC. So you get what you buy. That's the MicroLogic 1000, and they still make these fixed PLCs because they're very, very, very cheap, and they program in the same language that the big guys program in. So you don't have to teach your programmer a different language to program these. We do have some microcontrollers out there, like the Arduino, which programs in a text-based language. Those guys are only like $26 a piece if you buy them from Jamico. So those are popular, but those are real, real hard to learn how to program because of the language they program. Okay, that was me. Somebody I fed back. So fixed PLCs still out there. I'll show you all this when y'all get here. The Boss trainers that we have, the Amateur Boss trainers, use fixed PLCs in there, but they'll never need to be expanded. They do what they do, and of course, if you're never going to change things or expand it, then fixed PLCs would probably be the route to go. Then we have a modular PLCs. And what we do is, first of all, we buy the CPU that we want on most of them. So we get to, and if I need to upgrade, I can upgrade to a different CPU. Here's the power supply, and then we buy modules. We buy input modules, we buy output modules, we buy analog modules, we buy communication modules. So if I don't want to use the communication that's built into the PLC, I could go to Ethernet IP or DeviceNet or all these other communication protocols, industrial grade communication protocols that's out there. So what's nice about a modular PLC is basically like a desktop computer. You buy what you want. You buy and you can upgrade them if you need to. This is a very small PLC. It's only got four slots in the rack. So what we did with a modular PLC is let me jump ahead a little bit. So what we did with a modular PLC is we have what we call a rack. And then the rack we insert modules in. But it's up to you to decide which module you want to put in there. So they have we call it a backplane, if I can find it. You can see this, there's a lot to this. And I want to show y'all that now so that, oh, I don't see it, guys. So this must not be the most recent version. Let's see, so where was that? So we have a microprocessor. All this would be considered to be the CPU, even though in my days this was the CPU right here. But on PLCs, all this is integrated onto a single circuit card and either built internal on a fixed PLC or on most rack mount PLCs, you get the ability to choose your CPU. We have read-only memory in there. We have random access memory. We need to learn those. We have a peripheral interface adapter. Undoubtedly, this guy came up through Motorola PLCs. Motorola microprocessors. The 6800, 68000. They call it a PIA or peripheral interface adapter. This would come out here and would actually connect your input. A buffer, by the way, is a go-between, and we'll look at that. So what we're going from is an industrial environment into a computer environment. We're going from a really heavy, electrically noisy environment into a computer environment that don't like a bunch of noise. So we got some type of buffer in there, or go-between between the inputs and the outputs. And then we have an address decoder, which they don't really show, would actually come up and select the actual device. So what we would do is we'll have a portal right here, and then each portal would have an address. And then address decoder would actually select the actual port that connects to the buffer. So the microprocessor is the brains of the central processing unit, brains of the computer. But in my opinion, we think these things are smart, but the only thing the CPU or the microprocessor can do is run programs. We are the people who currently write programs. So in my opinion, the brains of the computer is the programmer. Even the basic input-output system, what happens when we turn the computer off, was written by people. So every program inside that computer is written by people. So everything you do, everything you see that these computers are doing, are programs that are currently written by people. Of course, artificial intelligence eventually will write their own programs, and that's going to be very, very interesting. But right now, these are PLCs. Right now are human. The brains of the computer are the programmers that set up this thing. All the processor does is run programs. So it carries out and executes program instructions. That's all it does. The only thing it knows to do is that when we turn it on, it's going to go into this memory right here looking for its first instruction. And then from that, after that, it's under the control of a program. So registers, in the book uses this term wrong. So we have an instruction decoder. we have internal buses. Now we have what we call caches, and we'll look at that in a minute to get y'all. So when we start looking at the specifications of a microprocessor, they talk about the levels of cache it has. Originally, when the processors first came out, the processor would be fit in two phases. It would go into the fetch phase, and what it would do, it would select a memory location. It would go out there. Inside that memory location would have to be an instruction. It would bring that instruction back into the processor. It would bring it into what we call the instruction decoder, decoder unit. It would say, okay, we want to do something. Then the microprocessor would go to the fetch phase. So then it would go back out and do something. So this would be like you going. So I'm giving you instructions, and you got 50 mailboxes out there, and you go to the first mailbox, and this is the way it used to work. And you'd open up the mailbox, you'd get it out, you'd bring it back into the house, and you'd give it to the instruction decoder, which would be my wife. And she would read it off, and she'd say, well, you need the contents of the next memory address. So that I'd go walking back out, and I'd go to the next mailbox. I'd pull that information out, which would be what the instruction wanted it to do. I'd bring it. So now we're in the fetch phase. I'd bring it back into the house, and she would look at it, and she says, okay, well, let's do this. Now you need the next mailbox. So you'd be going out and coming back and going out, fetch, execute, fetch, execute, fetch, execute. What they finally realized that just about every program, and we'll see that, just about every program eventually loops. So if I could go out there and start pulling in, so instead of me going out there and getting one mailbox, I would go out there and get 10. Then I would bring them back into the house, and I would put them in my cache. And my wife would look at the first one. It says, okay, go to the next mailbox, but the next mailbox is in the cache. So she'd go there, she'd go there, she'd go there. She runs out of space, and she says, well, I need something else. Well, then I'd go back out to the mailboxes, and I'd pull in 10. Instead of getting one, I'd pull in 10. I'd put them in my cache. And then eventually, the whole loop will be in the cache. And now instead of going out every time, we're inside the cache of the processor. And the only time we would have to go out if we change the program sequence. So this is what the cache does. The cache holds prefetched instructions and prefetched data. And once they added this cache to the processors, that's when the speed of the computers, they jumped twofold. I'm probably tenfold. Because of constantly having to go out there and getting the information out of the memory outside the computer. The registers actually hold the instructions while they're being executed by the arithmetic logic unit. So the arithmetic logic unit is what does the math and what does the logic, and also the shifts and all the other kind of stuff. So registers are inside the microprocessor. The book calls stuff outside the microprocessor. It's going to start calling those registers, but that's not true. They're going to be data files, and we'll look at that and make sure we get that corrected. So if you ever get inside the actual documents for the actual processor itself that's provided by Allen Bradley, they don't use the term register. They'll call them data files and data bits. So we'll try to correct that in the book because registers are inside the processor. So instruction cache temporarily hosts prefetched incoming instructions. The data cache temporarily hosts incoming data that the instructions are operating in. And once that processor loops, then everything's inside the processor, and now the processor can scream through those programs. So every one of our processors now have cache memory in them. Somebody gonna ask the question? Well, the dial-up, we use modems. And modems on dial-up, yeah. No, this was before. Modems were way back there. So modems, we literally modulated the data. And the highest speed that we had available at the time was 9,600 bits per second. So think about your access now. When you come through your cable, you're up to I think Spectrum guarantees 200 megabits per second. So now that means something. So dial-up, the best we could do was 9600. And then we got up to 96,000, but it was using some compression techniques that are used all now. Everything you get now is all compressed, and then when it comes into your computer, it uncompresses it by doing algorithms. So it's really, really neat. So our transfer rate is actually faster than the media that it moves through because of the way they do it. But that's a really good question. Yeah. So caches were added. I think the first cache I remember was with the P8 processor, the Pentium 8 processor that Intel put out, and that was the first time they had 2 levels of caches. I'll show y'all the actual mask for the i7 processor, which is still a very viable processor put out by Intel, and it's got 4 levels of cache in it. So it's got the cache feeding the cache, which is pretty neat, and so it keeps moving up the chain. But you can see having those caches, it eliminated all that fetching from memory, actually going out to the real slow memory. So we run the memory in your computer is very slow. It uses a type of memory called dynamic memory, which is really, really slow. But using the cache, it allows us to use that slow speed memory in your computer now. So that's a good question. So here's the die for an i7 processor, 758 million transistors on a 1/4-inch wafer. Here's the caches down here at the bottom. So it's got 4 levels of cache. It's got 4 cores in there. So it's actually got a core is actually a microprocessor. So it's got multiple micro. It used to, and I'll show y'all this. The first file server the first domain server we had actually has 2 microprocessors in it. That's what we had to do. We had to use multiple microprocessors. Well, what they do now is they put multiple cores inside on a single wafer, which has really, really boosted the speed if you run the right programs. I don't know if we have time to call threads because we don't run that in the processors that we're running now because of the programs that they're running. So, but that's a really good question. But yeah, you can actually see these, and you can actually see the 3 processors up here inside the core. In fact, this is the actual block diagram of an i7. So it's literally got 4 processors in there. And now they're adding graphics processors. So that's some big thing where you got processors inside one chip that's actually doing nothing but processing graphics that's going up to your screen, which is pretty interesting. So now we have processors running your program, and then processors running the video inside that. So they'll talk about so many processors and so many GPUs, graphics processor units. But the programs have to be taken advantage. So this is the buses. So we need to understand this. So a bus is basically a group of conductors where like information moves inside the computer. And of course we have 3 buses. We have the address bus, the data bus, and the control bus. The address bus is used by the processor to select a device, memory or input-output for communication. So the wider the address bus, the more things the microprocessor can select. The data bus, so the address bus is a unidirectional bus. It comes out of the microprocessor, and it's what the microprocessor uses to select. Then we have a data bus. The data bus is a bidirectional bus. So it means it can communicate in 2 directions, but not at the same time. So they're what we call half duplex. Transfers data between the device selected by the address bus within the NPU. Transfers data between CPU components, such as between I/O and memory. The wider the data bus, the more data that can be transferred at one time. So standard bus width now is 64 bits, and that's what they say. It's a 64-bit processor. So that means it's transferring information with the outside world using 64 bits. Actually, most of the new microprocessors, the address bus is 128 bits. So it does 264. It does 64 bits per transfer to load the cache, which is really, really neat. These guys really screen. Then we have what we call the control bus. The control bus controls the flow of the information between the address, the device that's selected by the address bus, and the device. So it controls the flow of information. It tells it what direction. There's a lot to the control bus, and this is why you got so many pins on these microprocessors. You got 128 pins for the address bus. You got 64 pins. You got 32 pins for the address bus. You got 128 pins for the data bus because it does 64 bits per. It does 128 bits per transfer, even though it's only processing 64 bits at a time. And then you got a control bus that controls all this flow all the time and making sure everything's at the right place at the right time, moving in the flow, interrupting, trying to get the microprocessor attention. So the control bus is very complicated, and each pin on the control bus. So some of them are out, some of them are ins, some are bidirectional. So the control bus is a very complex bus. So this is a block diagram of a basic processor. We have the microprocessor, we have memory. Basically, it holds the program that the processor is running, and also it does hold some information. Then we have input devices which are running really slow. So the processor is screaming. The input ports, and you think about how fast you can type or how fast you can punch numbers on your keyboard. So here you got a microprocessor that's living in a nanosecond world, and we're over here in a millisecond world or a second world. Well, you got to have some way to compensate for that speed. So we move through portals. We have input ports, portals. A portal is an entryway and an exit way. And then we have output ports, and we have I/O ports. There's actually 3 different ports we could run into. And so the address bus is selected to everything. So they select every port, everything. Then the data bus is where the actual data transfers, and the control bus controls the direction. And there's multiple pins. I've only shown 2. A good analogy of this would be this diagram that I drew, by the way. And what this does is this gives, so I've got a 3-bit address bus. So 3 bits means I can select 8 different things. And we looked at that. So right off the bat, the size of the address bus. So here I'm only 2, so that means I can select 2 to the 3rd. So that's 8. So I've got 8 mailboxes down here. So my address decoder would be in here. So what would happen is your address bus would output an address. So here it's outputting a 4. That's a binary 4. So this comes down. All these mailboxes say, well, this don't belong to me. This don't belong to me. This don't belong to me. Hey, this address decoder, and this guy says, well, that's my mailbox. So what does it do? It opens its door. So the address bus allows us to access what we call a port. Then what happens is we have to tell the mailbox what we're doing. So here I come up here and I have a control line that says I'm writing. So this tells the mailbox to take whatever's on the data bus and store it into the mailbox. And then it outputs another address and that door closes. It's real fast. So that would be what we call a write cycle. So this control pin is what we call the read-write line. So every one of them has a read-write line. So it tells the device if the processor is reading or if the processor is writing. So if it's writing, the memory location or whatever is going to take that information and use it, whether it's a mailbox or if it's memory or whether it's an input or an output port. And then this tells it this. So the address selects, the control bus tells it what it's doing, and then the data bus is where the data is transferred. So that would be what we call a write cycle. So this is a read cycle. So here we're outputting another mailbox. So that says mailbox 6. So down here, the mailbox that has that address would open up its door. This guy now, the control bus says, I'm reading. this would tell the microprocessor, this would tell the memory to put information on the data bus because the microprocessor is reading. So we looked at two basic cycles, a read cycle and a write cycle, but you got to understand, we got a 16-bit data bus, address bus, so that's 65,536 addresses this guy could put out, just for I/O. So we're still dealing with a 16-bit I/O address bus that selects input output. That's 65,536 ports I could have out there. But we got to tell these devices what we're doing. So the address opens up the mailbox. The control bus tells the mailbox what I want to do, and the data bus is where the information is actually exchanged between the device and the microprocessor. It's pretty interesting. So hopefully that explains the address bus and data bus. So the bigger the address bus, the more things you can select. The bigger the data bus, the bigger communication we have. And usually that's what they're doing when they define a processor, is they're saying, what are we communicating? And so a 64-bit processor means that the data bus has got to be at least 64 bits. Terms. So we got an instruction. This is a command given to the CPU that is specific to perform a specific task. An instruction set is a list of all the instructions supported by the CPU, or the programming language. So we're going to program in a high-level language that the microprocessor, the CPU, has no idea. So we're going to have to translate it. But the instruction set, so we'll go and we'll look at the instruction set for this 1100 PLC, and it'll show us all the instructions that we can write in a high-level language. I need to figure out, so let me pause this. Let's go ahead and take another 10-minute break, guys. This is not the actual. This is the slides I wanted to show y'all. So for some reason it didn't update on my file server. So we'll drop back and look. So this is a rack mount. So this would be the actual rack. This is the rack for a 500 series PLC. So we have all these slots, and so you'd slide a card down in here, and I'll try to get one of the 500s over here. I don't know if I can do it. Then what we have is every card or module, we call them modules, not cards, plugs into this bus down here. So this is actually a bus. Power comes down through here. Address comes down through here, but it's through an address decoder. We'll talk about that. And then the cards plug into these slots. This one, you see it's got two connectors on it. So this one is the CPU. The CPU would always have to go right here, and then you buy whatever cards you need to do it. If you need inputs, you'd buy input cards. If you need A to D, you'd buy those cards. But this would be, they buy these in different slots. The one on this one right here would only have 1, 2, 3, 4 slots. So it's 4 slots is available. The one we have is a 7-slot rack, even though we've only got 2. We got the CPU, and then we've got the 2. We got an input card. We got a 16-bit input module and a 16-bit output module, and we'll talk about that. By the way, on these, so we start, and we're going to find this out. In computers, we start when we deal with addresses, we start from 0. So we call this slot 0, and this is where the central processing unit will go in slot 0. And then from then on, in slot 1 through slot 6, you put whatever type of module you want in there. And then when we write our program, one thing we have to specify is what slot. The part of the address is what slot that the module's in. And we'll look at the addressing scheme. ArchLogic 5000 has changed it a little bit, but it's pretty easy on ArchLogic 500 to figure out the address and how to address slot 1, slot 2, slot 3, slot 4, slot 5, and slot 6. The CPU is slot 0, so you don't address that, it's just there. But when you specify where the inputs are and the outputs are, This is so we've added one. So we're going to call this a rack-mounted modular PLC. So this guy actually has a rack, and then it's got a back plane that carries all the buses down through where each one of your cards plug into. This is the newer type modular PLCs. I refer to them as hybrid PLCs because why I call them hybrid modular PLCs is they have some inputs and output ports built into them. So the CPU and your and internal inputs and internal outputs are all in one unit. And then what you can do is that there's a connector on the side. I don't know if I can pick this up. Yeah, we would take off this cover right here. Oops, sorry. Let me find my camera. So we would take off this cover right here, and then we could add modules onto this. And the back plane literally comes down through the PLC, so we don't have a separate back plane. The back plane is actually integrated into the PLC. And these guys usually mount on what we call a DIN rail, and these are standard sizes, and this is called a top hat DIN rail. You can see because if you flip it upside down, it kind of looks like a top hat, and it's got these grooves, and then the PLC latches into it. So to take the PLC, you just undo some snaps and you snap it off, and this would be wrong. And what's nice about this unit is we can mount any PLC on it that mounts on to a that mounts this way. So this guy here's got certain inputs built into it, and it's got certain inputs. It's got a number of internal inputs built into it, and a number of internal outputs built in out of it. By the way, it's only 24 volts, so I'm not worried about getting shocked. The 1100, the 1000, excuse me, uses 120 volts on the output. So if you get on one of those, don't open the covers. Here, the actual inputs and outputs are exposed because they only run on 120. I mean, they're running on 24 volts DC, and we'll talk about that later on. But so this is a hybrid PLC. So you can use it as a fixed PLC if you don't want to expand it, but you can actually add modules onto it by snapping them on this DIN rail. Open up this cover, pull it off the side, snap it in there. And push it into a connector, and then it'll latch in. So you'll have to. It's not hard to get. It's a little harder to get on. So these are really popular right now. So every PLC that we have in here, are except for the 1000s, are either rack mounted or they're these hybrid modular PLCs. And then Allen Bradley puts out one called the Control Logic, which is it's a rack-mounted modular PLC. So this is still not the current ones. I wanted to show you that. This one right here, this is the SLC. We call them SLIC. I don't know what SLC stands for, but we call them SLIC 500s. These are no longer available. You can't even get modules for them anymore. So Allen Bradley has replaced this with their Control Logic, which is their rack modular PLC. So we look at this, 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 looked at this, went through that. So an instruction, this is a command given to a computer that specifies a specific task. An instruction list lists all the instructions that the CPU or programming application for the CPU or programming application. A peripheral is any device that communicates with the computer through a port. So you probably heard that term before. An import, this is a portal that allows information to flow into the computer through a port, and that compensates for the speed between the outside world and the inside world of the processor. And it also gives us the ability to assign a port an address. To assign a device an address. An output port is a portal that allows information to flow out of the computer to the outside world. So if we don't have inputs and we don't have output ports, we don't have a computer. So, and you can see it. So on your computer, on your cell phone, your touch screen, that's input, that connects to an input port, at least one. your sound and your display. That's your output port that's in behind your touch screen. If you crack your screen all good, or your output stopped working, then you know, if you got a warranty on it, you might get a new one, or it's usually time to upgrade. An I/O port, this is the portal that allows information to flow in and out of the computer. But generically, when we talk about the ports on a computer, we call them I/O ports. Even some of them are strictly input, some of them are strictly output. So your touch screen that's on the top of your display, that's an input device. You're not outputting to that. It's clear. It uses a capacitive type sensor, and it's input. And of course, your speaker, the only thing a speaker on there is used to give sound, right? Your microphone, that connects to an input port. Hardware, these are the physical components of a computer. Software, these are programs or information stored in a computer's memory or peripheral that the users can change. So you can change those. Firmware, these are programs or information that is not easy for the end user to modify or change. These are usually stored in some type of read-only memory. Mass storage devices, these are usually read-write devices where we can hold information until we get able to load them into the machine. These would be your hard drives, your solid-state disk drives, your flash drives or your thumb drives, your SIM cards, and all that kind of stuff would be considered mass storage. They're not part of the memory of the computer, and that gets people confused all the time. So CIS, when we first came out with processors, we had one instruction for every task. Over time, they realized that we could combine tasks within a single instruction. This reduced the instruction set for the processor. This is binary instructions, and this brought about a type of computer called RISC processors. Do you need to know what type of processor runs inside your PLC? No. All you're going to do is buy a model. The actual processor, the actual microprocessor, you have no idea. All you're going to look at is the features offered by the processor. And as far as RISC and CIS, these are totally transparent to you. Anything above the Pentium processors, these are all RISC processors. And what it did is it reduced they realized the instruction sets were starting to get so complex. And then somebody finally says, well, we can make this instruction do 2 or 3 different things. Well, as soon as you could make it do 3 things, and that eliminated 3 RISC instructions. So most of our processors are RISC, but this is nothing to do with you. These are ones and zero. These are ones and zero programs. How they process data. We're going to look at it from an application point of view. You know, so is this CPU inside my a PLC, a RISC, or a CIS? It's not even on the data that comes with the processor. They might give you the speed, the processing speed, but they don't tell you that. One thing they do tell you though is the amount of memory. So we got 2 types of memory in the PLC. We got RAM, which is random access memory, and this is kind of all the memory is random access. But this is actually, I teach it as read-write memory. So this is the memory that you can store information into and you can get information out of very easily. So this is RAM. So all your PLCs have a bunch of RAM in there. Then we got read-only memory. Read-only memory, this is memory that you can read from, but it's very hard to write to. Originally, it was easy to do. But now we have a type of memory in our computer called flash memory. It's called flash ROM, which gives us the ability, it's actually double EEPROM, which stands for electrically erasable programmable read-only memory. So we can literally erase the contents of these and reprogram them. But you got to be really, really careful that it comes up and says, I'm upgrading the firmware in your computer. Don't unplug it or disconnect it from the internet. And by George, you better not do that, because what it's doing is flashing your ROMs, and that's your your automated nervous system. It's like the programs that you're born with. So that's ROM. Those are the programs that you're born with. Uh, that makes your heart beat, that makes you know how to breathe, you know how to see. So if you screw around with your your operating system, you could crash your computer or your phone and it won't do any good at all. Or if you interrupt when it flashes, so it'll let you know sometimes it says an upgrade is available, and what they're doing is they're flashing your ROMs, which is really neat. So I try not to flash mine. I try to hook mine up to a computer and actually do it over wired. I don't even like to upgrade my phone over wireless, because you can lose your wireless. So that's just a train of thought. That's what I do, and it's also faster. Static RAM, called SRAM, stores data bits and internal flip-flops, does not have to be refreshed to maintain data. We don't have much. This is your cache right here. These guys scream. Most of the memory in the PLC and your computer and your phone is called dynamic memory, DRAM. It holds binary data in a form of a charged capacitor. Basically, a capacitor is a little tiny battery that we can charge up, but the problem is that it don't maintain it very long. So what we have to do is kind of like your car battery that you would do if your alternator went out. I know people that's done that, where they just go out there every day and recharge their battery, and then they can run their car on their battery until they get back to the house and recharge it. So that would be kind of like that situation right there. And that's what your battery's doing anyway. It's just that it's being charged by your alternator. But if we didn't refresh dynamic memory, it would lose its content. Originally, we had to do it with programs. Then they came out with a DRAM controller, which basically does it for us. And now it's integrated into the chipset that's running your phone. So this is all the refresh of the dynamic memory is, and it lets us use the cache. So the cache allowed us to use DRAM for our main storage, which means it can get DRAM. If you understand transistors, SRAM takes 5 transistors per bit. DRAM takes 1. So what that means is I can get a lot more. I can get 5 more storage cells in the space it would take to get 1 storage cell for SRAM. So this DRAM, it's got the cache. The caches is what allows us to use this, because what happens is it only has to access that DRAM, and once it got it once, then it's constantly loading those caches. It's got these cache controllers in there. That's anticipating when you're gonna jump. So now we got look ahead, where the processor's actually looking ahead and seeing if your program's going to make a jump, and then it's going to come out of a loop and go into another loop, and it starts preloading from where you're going. So these caches allows us to use this very slow speed DRAM for mass storage, and still have an extremely fast computer. Thank goodness. SRAM would be so much more expensive. But that's the caches. So the caches inside the processor are static. They don't have to be refreshed. Data stored in DRAM must be refreshed every few microseconds due to the discharge of the capacitor. In your computers, we call this DDR for double data rate SDRAM. So if you ever upgrade the memory on your computer, it'll be like DDR2 or DDR3. I think they're actually on DDR4 or 5 now, and they're not compatible with each other. So if you want to upgrade the memory on your desktop, memory's not cheap, because we're dealing with gigabytes or terabytes worth of RAM, and it's not cheap. So a lot of people will start off and upgrade their memory, and that's another advantage of a desktop. If you know what you're doing, there's another advantage of a desktop, is you can upgrade it. I had a computer for years. If people walked in and saw it, they would think it was this old computer. But I've kept it upgraded. So I've put new motherboards in it, changed out processors, added memory, but it still looks the same, because I know how to do all that stuff. Data stored at SRAM remains unchanged until either new data is written over existing data or power of the chip is turned off. Does not have to be refreshed, can be accessed a heck of a lot faster than DRAM, and usually used in the cache memory of them. So this is the difference of the two. Mask ROM. A mask ROM, we don't see these used much anymore. Mask ROMs, the programs were actually put into there. So when you boot your computer, booting was telling it to load its operating system. It starts off, the first address it goes to, looking for a binary instruction, is ROM. And then after that, so that's the only thing that CPU knows what to do, is it knows to go to a certain address every time and pull in an instruction. And then from then on, it's under the control of a program that was written by a person somewhere. So mass ROMs, we actually bought these with the programs in there. They were actually put in there when the ROMs were made, and these were in there for years. So if you needed to upgrade your ROMs with your basic input-output system, the basic operating system that gets this thing started, you literally had to buy a ROM. So there was basically no real upgrades. Then they came out with a ROM, and we've got these, by the way. I can show y'all these when y'all come into class. We had what they call programmable ROMs. These basically, every storage bit was a little fuse. And then what would happen is that to store a 1 in there, you'd put it in a programmer. You'd put the ones and zeros in the memory of the programmer, and it would go out there and blow fuses. And once it blew the fuse, it would be a 1. If you didn't blow the fuse, it would be a 0. And that's where the term burning comes into play. So now we don't use that much, but they'll say, you need to burn new ROMs. Even when we deal with these other ones, now we call it flashing, because the ROMs are flash ROMs now, which is double EEPROMs. So we call it flashing now, but we use the term burn for anything above a mass ROM for years. Programmed outside of the computer in which it is to be used by a PROM programmer. And we've got one of these up in A210. I need to go up there and see if I can handle getting it down to class. Erasable read-only memory. I can show y'all these when y'all come in. These are glass. You can actually look in and see the actual wafer in there, or the chip. And you can't see the transistors, but I got a that magnifying glass that we used to look at the triads on the screen. We'll look inside a EEPROM. These we could reprogram them, but we had to erase them with ultraviolet light. So it was a real high intensity too. So you had to be careful. So it was all sealed up, and we'd put them on some anti-static foam and put it under there, and it would erase it. It would erase them in about 30 minutes. Then you don't see those much anymore. So what's happened is we've moved down to this electrically erasable, programmable, read-only memory, double EEPROMs, E-square PROMs. These are electrically erased and reprogrammed them. These are basically what's running in your USB drives. These are running in what we call solid-state disk drives. So they're not extremely fast. We don't call it burn them anymore. We call these flash ROMs instead of double EEPROMs. And when we change their contents, we call them flashing. But it's special. You can't do it. You got to have special applications. So you can't flash your ROMs in your computer. You have to have a special application. So now it'll send you a notice. So I get a text saying, there's an upgrade available to your iPhone. And then I'll go in and I'll plug it into I'll download it to my computer, and then I'll flash it. But we call it flashing now. I guess it's just a term. But these are double EEPROMs. USB thumb drives. These are double EEPROMs. But we call them thumb drives, or whatever you want to call them. Memory sticks, we call them that. SIM cards, these are double EEPROMs, where they can take them in, and your phone company can put that information in there. You know, now I think AT&T provides a program, an application where you can actually move the stuff from the SIM card in an old phone over to a new phone without even bringing them into. Used to, you'd have to bring them into one of these centers, and they would have to do the SIM card for you. But I think you can even do that now if it's not compatible. But it's got to be an iPhone to an iPhone. It can't be an iPhone to an Android phone. But these are double EEPROMs. Go by different names now. Flash ROMs. When you burn them, it's flashing your ROMs. There'll usually be a thing that'll pop up there that says, "Don't turn your thing off while this is occurring," because these are your ROMs, guys. That's your lifeblood. That's your automated nervous system in your brain. That's what you're born with. That's what brings the computer to life. It actually goes into those ROMs and starts running instructions out of what we call the BIOS, or basic input-output system. So just about all of them are flash ROMs now. All your PLCs are flash ROMs. They have a section of flash ROM in there. Especially if you disconnect everything and you turn something off and unplug it and move the PLC around, you'll come back in and and the program is still there. Then those are going to be in flash ROMs, or that means it's stored in double EEPROMs. There's still RAM in there, random access read-write memory, which is volatile. This is holding temporary information now, information that's being processed that you store. The status of your input ports, the status of your output ports, all that's going to be in the RAM inside the PLC. Your program is going to upload into RAM, and then what it'll do, it'll come in, it'll put that into the flash ROMs or the double EEPROMs inside your PLC. So that way you won't lose your program if you lose the battery in your PLC, or if you lose power to your PLC. MPUs used address decoder to enable ROM, RAM, and I/O devices and support chips. So this address decoder is what we're actually communicating with. So over here, I might have a 16-bit address bus, and then it goes to an address decoder, and this has come out a wire, and this allow me to select input port number 0, and then I'll have another one coming out of the address decoder that would allow me to select input port 1, and then we have the same way on the output ports. So that address decoder is allowing me to address outputs and inputs individually through my application. So we'll come up here and we'll type in an English thing that tells my address. The address goes out, goes through the address decoder, and actually ends up selecting a single input or a single output. So the address decoder monitors the address bus. It enables the address device, places data on a read-write from the data bus. The control bus tells the selected device the direction of the communication. Support chips. We usually refer to these as chipsets. So basically, you'll get the CPU, and then you'll have another chip on there. And I think I might have one of those. And I don't know if I have time to go pull it. I don't. I've got a motherboard that actually comes out of a computer, the actual desktop computer. And it's called, but the motherboard has everything on it. It's got the processor, it's got the chipset, which runs the actual motherboard. It's got your address decoder and all that kind of stuff in it. But we refer, this book calls them support chips. We normally refer to this as the chipset. So what we do is we come over here and we have an address decoder. And then the address decoder is going to allow us to address like an input. So we got an input decoder. And this is going to address a single input device or output device. Now out here, the problem is out here, this is an industrial application. Over in here, this is computer. So the problem is we're going from an extremely noisy environment into a PLC. We're going to something, an output port that might be able to switch 115 volts with a input voltage inside the PLC of 5 volts, which is pretty standard supply for digital devices. So what we do, and I've got that backwards, guys. So here's my 5 volts over here. Here's my 5 volts over here, 5 volts DC. Over here, what they're doing is they're inputting 120 volts AC, even though they don't tell you that. So what we do is I close the switch. So we're going to bring out the wires. We got 2 wires. I close the switch, and then this connects this to a rectifier. Now, in solid state, you'll learn how this thing works. But what this is doing, this is converting AC to DC. So you got one of these in your car. So we run an alternator, and my whole car runs off of DC. So you have a rectifier in your car that's taking AC and converting it to DC. Then we come in here, and we got to have a resistor right here, or the Zener would burn up. The Zener is a regulator. So over here, this might be 120 volts DC, but over here I want this to be 10 volts DC. Well, what we do is that this says 10 volts, and then this resistor would drop the rest of the voltage. So what I do is I'd end up with 10 volts. This runs through an optical isolator. Now, an optical isolator means we transfer the ones and zeros through light. So my input is not connected to the CPU. My input is connected to a photodiode. Not a photodiode, a light emitting diode, which y'all seen these. This comes over here and strikes what we call a phototransistor. So over here, this could be plus 5 volts. So I'm over here 120 volts. I go through an optical isolator, which means my input is completely isolated from my control system, my plant. And then we can bring that into our processor over here. So this would be a basic input port, DC, AC to DC, which is pretty neat. This image is not exactly right because there is no protection for the Zener diode. So we got to have what we call a series drop-in resistor that drops the difference between the input voltage and the regulated voltage. But we're isolated, completely isolated. So originally PLCs, most of your controls, when I first got into the business, were 120 volts. So a lot of your PLCs dealt with 120 volts on the input and the outputs. What they've done is they've came up, and we've came up with a National Fire Protection Association, and they've came up with what they refer to as 70E, which is a safety standard. What they've done is they've said that a lethal voltage is anything above 50 volts. So this has changed things. This has changed PLCs. This has changed controls. So standard, when PLCs use DC, what we use is 24 volts, which is half of the control voltage. So now the PLC is safe, and then we have relays and stuff like that. So 24 volts now. The 500s actually even use 24 volts. So that's pretty standard in PLCs now, newer PLCs. This would be an example of an output port. So we come over here. We output like a 1. That would come over here. This is protection. That would put on light. This would come over. This would come over and put out an output. This is pretty common also for output. So this would be a DC output, not an AC output. This would be a DC output. This is not in the book. This is more in line of what an actual input port looks like, an AC input port looks like. By the way, we can put DC over here. So we do have one where you can either put DC or AC on the input. So if I put DC on here, like if this is plus and this is minus, it would still flow in this direction, and then it would come back and go back to here. And if I put plus down here, minus up there, then it would flow the other way. If I put AC, it would swap between those two paths. So we do have some PLCs where you can put AC on the inputs, you can put DC on the inputs, you can put minus on one side and plus on the other. The 1100 gives us that. I mean, the 1100 gives us that ability. We can either put AC on the inputs, we can put DC, because this is the type of input ports they have. But what I want you to know is that whatever we put over there, the internal works of the PLC is isolated from the load by these optical couplers, which are pretty neat. And they're little tiny things. They're usually 4 pins, 2 for the input, 2 for the output. Very small things. And these have been used in PLCs since they first came out. This would be optical. I don't know what they mean by full wave rectifier, an optical isolator. We've already talked about that. So the optical isolator, this is inside the PLC. You don't see it. In fact, this is where you're at right here. You're over here. All this would be part of what we call the input bit for that port. And what you do is you hook up 2 wires, and we'll show you how to do that to an input port bit. We call it an input port, but each port right now is only a single bit. So this, we talked about the Zener. Of course, we know what that does, and we know we got to have a resistor right there. So this is not quite correct. This is more correct right here. So Zener diodes, what it does is it allows us to bring in a high input, and it drops it down to a voltage that's compatible with the and what's nice is that this says 120 volts, but as long as it's above whatever voltage this is, I could actually come in and put 10 volts AC out here, and we'd still get 5 volts over here. So here they're saying 120 volts, but most of these AC input modules give you the ability to put a wide range of AC voltages on this thing. Optical latch, we're not going to look at that. Triac. A triac is an AC. We call them solid state relays. So what a triac does, it allows us to control AC electronically. So we come up to the output, and what we do is we trigger the triac, and then it'll act like a closed switch, and it'll allow us to run AC loads. Now look, this is an address right here. So what I would do is O, what do you think O stands for? And then we come up here, we put a colon. And then we come up and we define a slot number. So this would be slot 0. So this has got to be a hybrid PLC. So on a rack PLC, slot 0 is occupied by the CPU. On a fixed PLC, the CPU does not have a slot. So your first I/O device would be at what we call slot 0, even though internal. And then we put a slash, and then we'll put a bit. So this is the bit address. So O means out, followed by the slot number, followed by a slash, followed by the bit address. So all our inputs are single bit inputs and single bit outputs. So what do you think I would put for N? I'd put I, then I'd put colon, and then I'd specify a slot number, like slot number 1, then I'd put a slash and specify a bit. So that would be in slot 1, bit 6. So that would be on the 1100, that would be the first module on the right. So here's some different outputs. By the way, we do have what we refer to as a relay output. So a relay uses an electromagnet, and we'll show you all these too, so I need to be making me a list. So anytime we put current flow through a wire, it creates a magnetic field. If we come up here and put a plunger on that thing, or an armature, when I create the magnetic field, then it will cause this armature to move. If we connect contacts to that, then what we've got is we've got what we call a relay. So a relay is an electrically controlled switch. Now what's nice about the contacts of a relay, it don't care what you put on them. You can put AC on them, you can put DC on them. Even though over here this is DC, what's flowing through here would be a, we had a guy, God rest his soul, he's gone now, but his starter, his key went out on his riding lawnmower. So he went out and bought a regular wall switch that you use to switch the lights in your house, and that was his starter. So he'd flip the wall switch, engage his starter, and when it stopped, he would turn it off. So he didn't even have a key. It had a regular wall switch on there, and that's what he put. Because it don't care. A wall switch don't care if you put DC. It don't care if you put AC. It's just a switch. So yeah, you could use that as long as you don't exceed the voltage rating on the thing and the current rating on it. You could switch DC with that. You could switch AC with that. Of course, with a wall switch. So a relay is an electrically controlled switch. So that's what you got in your car. So you got a relay box out there in your car. It's black. It's usually over there by the battery. You pop it open, you see all these little black cans or these translucents or whatever. Now those are nothing but relays, because that little button you push on your dash to turn on your headlights, that little button could not handle the 10, 15 amps that is required by your headlights. But what we can do is we can take that thing and pull in a relay coil for using milliamps, and then it closes a switch that controls, 10 or 15 amps. So the starter on your car, it's got a starter relay. It's built into the starter. It's really, really neat. There's no way in the world your starter's running through your ignition switch. And of course now we've got push buttons where you don't have a key, you have a fob that you carry around in your pocket. And when you get close enough to your car, you press a button and it starts. Well, there's no way in the world that button's going to control your starter. It's going to be a relay. But what's nice about a relay, the contacts, we call them contacts, they can be AC, they can be DC, they could be almost anything that it's controlling. 120 volts AC, we'd look and see that. So both the 1100s and the 1000s have relays, and you can actually hear them click when you turn on an output port. You hear it click. So on the 1000, which is this guy right here, so on the 1000, if I open this up, here's Alabama Power right here, line 1, line 2, and you can see they're jumping this over to the commons. Okay, so this guy right here is 120 volts if it was turned on. So that's why if you use one of these, we don't want, because it's got relay outputs. I could come in and modify it. I could take the 24 volts coming out here, and then I could run it down here, and I could switch them over to 24 volts. The only problem is that none of these lights would work, because all those lights are 120 volt lights. So that would be the biggest problem with me. Now it would be a lot safer, but I'd have to go over there and buy a bunch of 24 volt lights and replace those, which would be good. Or I could unmount it off this guy and move it over here and run them off 24 volts. So this is the same thing. It's got relay outputs. Here we're taking DC and running the commons. So here we're using DC on the actual coming out of the Edu-trainers. So relay outputs. These are the advantage of relay outputs is that we can use DC. They can control DC. They control AC, multiple voltage levels. 5 volts, which is pretty popular. 24 volts, which is very popular. 120 volts, you'd still have those out. The biggest problem we have with relays is they're slow. So we could not run a high-speed output like a pulse width modulation outputs or a pulse train outputs. Relays just couldn't keep up with that. But running standard loads, they have no problems. So relay output. So we could have a DC output, We could have an AC output using triacs, or we can have a relay output, and we get to decide what our outputs are going to be. And what's nice about these is every output has a common. So what that means is, since every output has a common, you can make one output DC. So every output has a common. So I've run my minus out through here. I'm sorry, I've run my plus out through here. Even though it's a black wire, that's all I had at the time. And so I ran it to each common, but I could take this one off and run 120 volts AC. So on this PLC, one output could be AC, 26 volts AC in an HVAC system. The other output could be 24 volts DC. The next output could be 5 volts DC. The next output beside that could be 120 volts AC. So this is really unique as far as these MicroLogix goes, is they give you with relay outputs. Now, if you buy DC outputs, you got no option but DC. If you buy AC outputs, then you got no option but whatever AC is designed around. Then we got digital analog. Like I said, this guy here has got two digital analog ports on it. So it's got a digital analog converter. I didn't want to do that. Where's my camera at? I don't know if we can zoom in far enough on this. So these are two. If it zooms in, it says analog right there. So this has two analog inputs right here. And what the A to D converter does, it brings in an analog input, and then it converts it into a binary number that represents that value. By the way, these are 0 to 10 volts, and they're 16-bit. I'm sorry. No, they're 10-bit. So it would take a voltage, 10 volts. I would get a count of 1023. And then it's up to your program to decide what the analog means. So 5 volts, I would get a count of 512. If I brought 5 volts in, that means if I got 5 volts, then I'd get 512 would be my maximum count. So that's what we do. It's got an A to D converter in it that takes a analog input and converts it over to a binary number. And each number would represent a count, or would represent a certain voltage. The only PLCs that we have that has an analog output, and I don't have one of those out here, so what we would do on those is we would store a binary number into the port, and it would convert that over to a voltage, depending on what voltage you have available. So analog to digital, this allows us to bring an analog input into the PLC. It converts it over to a binary number. The Siemens PLCs have, oh good gracious. So these are 10-bit. They have 12-bit A/D converters on it. So that means we could take this could convert it into a number up to 1020. Count up to 1025. No, 1025. 23. Yeah. 1023. It's got a 12-bit, which would be 4096 or 4095. So it's got a higher resolution than that. So yeah, the Siemens 1214s that we have, that if you take the PLC3, the ILT212, you'll deal with those, and they got 12-bit A/D converters on them, which is neat. Allen-Bradley programmable controllers are used to implement specific instructions: input, output, timing, counting, data manipulation, reporting, arithmetic, logic, and communications. The logic we're going to do is going to be what we call relay logic. We're going to do it with contacts. If you take, so this is as far as we're going to get in this class, is input, output, and then timing and counting. If you take PLC 2, which is ILT 196, that's been taught in Miniterm 2, then you'll get into these other things that we can do. The computer things, the actual computer stuff that we can do. Programming, computer language, program, programmer, source code, driver, instruction, machine language, assembly language, and high-level language. These are some terms that we need to understand. So machine language, this is the only language that the microprocessor understands. It is a binary language. All other languages have to be translated. So the only language I can teach is I can talk is Southern English. So that means if I went to Germany, I would not understand a thing they were saying unless I had a translator. So we went to Germany, but believe it or not, all the Siemens schools are taught in English, which is pretty neat. But every once in a while they would break apart. Nancy learned how to cuss a little bit in German. Hoyt spent a lot of time on the job he had before he started here, and he's got a pretty good German vocabulary. Me, I don't know that, so that means it has to be translated for me. So machine language is a binary language. So what we call operational codes. These are binary codes that we would look up into an instruction set. I've got the instruction set for an 8-bit processor called the 6800 that I'll try to show you. By the way, machine code programs are referred to as object code programs, so that's another language. But a programmer that programs this, they got to know everything about the microprocessor. They got to know the registers. They got to know the capabilities. They got to know the syntax. They got to know the addresses. Everything inside that computer, the programmer has to know everything, which is very, very complicated. The first language I learned was the machine language for a Motorola 6800 processor, and it was an 8-bit processor. So its instructions were 8-bit, so it only had 256 instructions available, a possibility, but it didn't use all the codes. And so we had a trainer, and we had to know everything about it. So this is an example of an 8086 machine code program. Just a bunch of ones and zeros. Means nothing to us unless we know what phase the processor's in. If it was in the fetch phase, we know that there would be instructions. Execute phase, we don't know what they are. But this is machine language. This is the only language the microprocessor understands. How many could program? I don't know if anybody programs machine language anymore. Assembly language uses mnemonics to represent instructions translated into a machine language by a machine language program called an assembler. So we would take our assembly language, we'd run it to an assembler, and it's a machine language program that would look at the ASCII codes and convert it into a machine language program. Even though still complex, it's easier than machine language. The programmer still has to know the registers in the processor's capabilities, instruction syntax, the assign and memory addresses. So this would be an example. This is the same program written in assembly language. Now it moves toward, I know MOV, that would be the instruction to tell it to move something. And it's going to move a register called the contents of an AX register inside the processor into an address 1020H, which is hex. Now, even though this is still very complex, I got to know all the registers and the names of the registers inside the processor. And this was an Intel processor, by the way. I'd have to know where this is at. I'd have to know this. I'd have to know what parentheses means. I'd have to know the right syntax for all these. It's a little easier, but it's still very, very complex. We have a language called instruction list that we can program a PLC in that's very, very similar to this, and it's very seldom used. After this, we have what we call high-level languages. This is what we're going to learn. Written using terms and expression common to the English language or the trade. Does not require knowledge of the microprocessor or addressing. Translated by either an interpreter or a compiler. Some high-level languages used by PLCs, ladder. This is the most widely often language. This is the one that we will learn here. This is the one we'll look at in PLC 2. This is the one we'll use in PLC 3. We have what we call structured text, which is kind of like Java, if you've ever been in that, or C or Pascal, these text-based languages. And what this does, it gives an avenue for people that's in computer programming, true programming, not coding, which a lot of students, we actually teach coding here to, if you wanted to learn how to make applications for an iPhone. In fact, it's sponsored by iPhone, by the way. It's a really neat program, but they teach coding here to write applications for iPhones. But structured text is which true programmers. So, writing true programs, except games and stuff, that's all visual in nature. Function block programming, this is very familiar with digital. So if you came up through electronics and digital, this would be available to you. In sequential flow charting, this would be a language that a programmer would understand if they understand flow charts. So these are the basic language. Structured list is not even on this list. That's a very, very complicated language because you have to know so much about the processor. So this is basically an interpreter. So we have our program written in a high-level language. So what I've done is this would be a basic. So this is basic, by the way. So I start off with the program CLS clear string. Input means I want to get something from my keyboard. D is where we're going to do math, and then print is going to send something to my display. Well, what an interpreter would do, it's got all these machine code modules built into it. And when it says CLS, it'll come up here. This will come in as ASCII code or Unicode. Interpreter would say, okay, I want to do CLS, and it would cause the clear screen module to run. Then the next input, the interpreter would read these ASCII codes or whatever code it is. It would say, okay, this means I need to make this module right here run. But an interpreter never generates a true machine language program. All it's doing is it's got all these modules in there, and it causes these little routines to run depending on what the program wants it to do. So you never end up with a true machine language program with an interpreter. Most of your simulators run this. I'm going to introduce you to a simulator called Logic Pro, and it's interpreted. So we never actually get a true machine language program. A compiler, what the compiler would do is it would take the high-level language program. The compiler would find the module and actually include the module inside a machine language program. So a compiler creates a standalone machine language program is created. RSLogic 500 and 5000 compiles the program as it's downloaded into the PLC. So the PLC never sees your high-level program. It sees a machine language program. And we can uncompile it too. So we can take a compile program that's inside our PLC and we can upload it into our computer, and it will the uncompiler would give us the high-level language program, which is pretty cool. So that's neat. The compilers that I ran into would not do that, but all our PLCs will actually uncompile a compiled program. But you actually end up with a machine code program. These guys are extremely fast. Interpreters would be like I'm trying to give a speech, and I've got an interpreter there, and I'll say a few words, and they'll convert it to Spanish, and then I'll say a few words, and they'll convert it to Spanish. That would be an interpreter. A compiler would be, I would take my speech, the compiler would take my speech and would convert it over the entire speech over to Spanish, and then they would give the speech in Spanish. That's what the compiler does. So the compiler is a lot faster. It's just that if we don't uncompile it, if we don't have the ability to uncompile it, the machine learning program doesn't mean any sense. But like I said, PLCs, both our PLCs, RSLogic 500 will uncompile for you, and also RSLogic 5000 will uncompile for you. So that's the program. I should have put that first, by the way. This is the language. This is ladder language, and this is basically came up through electrical. So in motor controls, you will learn ladder diagrams. And the way ladder diagrams work is we have two power rails, but in the PLC there's actually no power. These are all simulated. And then we draw circuits between here. And each one of these is referred to as a rung. And you can see how it's got that name, ladder. So we draw circuits between this rung right here, which is generically will refer to L1, and this right here will generically refer to as L2. So this is saying that we're coming through here, and it says get whatever's coming in on input. Input. This is Siemens, by the way. Input slot 0, bit 0. This says okay. This is normally closed. We'll look at this or examine if open. So these are actually coming from input devices. So on my PLC, I'd have a common, and then I would come over here and I would hook it up this way. By the way, this is the symbol for a DC source. The little line represents the negative, and the long line represents a positive. Now originally this was for batteries, and each one of these represented a cell. But now on a electronic power supply, we just draw usually this many. And then what we would do is we would take this, and then I would run this over to, let's say, a push button. The push button would come over here and hook up to an input on my PLC. Let's do Allen Bradley. So Allen Bradley, I would come over here and I would say input, and it's a fixed PLC or a hybrid PLC, and I'd say input 0/0. And then if I press this button, then this simulated contact right here would close. This is not real. And then if I wanted to hook up another output, I would take this common. So this is our common. So your common does not have to be a minus. It could be any. And then I would come over here and I might hook up another push button. And then I would take a wire and I would hook it up to another input port. Let's say input : 0/1. And now when I close that one, then this contact right here would change. So these are three inputs. We're using bit 0, 1, and 2. So I would have something hooked up on the input ports of the PLC. This, for this PLC, it's actually going to be two parentheses like this. This represents an output port. So this is output. On ours, on Allen Bradley, I'd have a wire, and I'll come over here and hook it up like this. And we'll talk about the difference. And then I would run this to all my output devices. And then this right here might be a light bulb. I'll hook it to my common, and then I would hook this up to output. Let's say output, that's a O. Let's say 0/0. So when this right here, this simulated coil, it's not a real coil, when it goes true, this output would put a 1 out and my light would come on. So what we're doing is we're running a common. So this right here, by the way, this outputs runs a plus going to the PLC and the minus going out here to my output devices. This could be a solenoid. It could be a relay coil. Now out here, you're going to use the symbols that's used by the electrical trade. So you'll have to use the symbol of a push button. You'll have to use the symbol of a light bulb. You'll have to use the symbol of a solenoid. You'll have to use the symbol over here. Inside here, we got very few symbols. We got inputs, we got contacts, and all these inputs are being controlled by something hooked up to a port. But we'll show you all that. And then we'll have an end rung. The end rung tells the program to come up here and just loop. So this program is just constantly looping. We call it a scan. But ladder diagrams. So we just draw circuits using these symbols, and these will be the only symbols that we start off with. We'll start off with these. Now for an input device, this is called an examinative close, and this is called an examinative open, and we'll talk about that. If it's a contact, so I could come over here and let's change this. Let's call that. Let's come over here and I change this to output, which is a Q 4.0. Well, that's not an input device. This is a simulated contact that's being controlled by this coil. So that means when this guy goes true, then not only does this guy come on, this right here also would cause this contact right here to change states. And like I said, we'll look at these. So that contact would open. So we can, if we give an input instruction the same address as a coil or an output, then it's controlled by that. If we give this symbol the address of an input port, then it's going to be controlled by a push button or whatever. And we'll get into that. But this is ladder language, guys. This is over in the United States, probably 95% of the programs written for PLCs is written in ladder. Germans, they like function block. They love function block. And then you have programmers, they like instruction, they like structured text. So it depends on where you're at, but what they've done is they've given multiple programs for programming applications. So we run an application on our computer. We run a programming application that allows us to draw these circuits, and then we download them into the PLC, and it's compiled. An operating system. Let's see what time it is. Almost there. An operating system, this is a machine language program containing all the drivers and shells that controls the computer hardware devices. So every computer has an operating system. So you're looking at my computer. This is Windows. So I'm running the Windows operating system. This is Windows 7. On my computer at home, I'm running Windows 10 because I got it free, by the way, by upgrading. So an operating system, this is a machine language program that allows, and then, I'm sorry, this is not, let me discard it, and let me change this right here. This is the operating system shell, so somehow a word got left over. So we have a special program that we load called the shell. The shell is the application that allows you to control your operating system. So this allows you to load programs. It allows you to touch a key. It allows you to scroll your screen. It allows all those icons to appear on the screen. So it allows you to control the operating system. The operating system is a machine language program. The shell is a machine language program. So you're looking at my shell. So I go back here, right here. Let me go all the way back to my... So this is my shell. This is my operating system shell. This is called Explorer. This allows me to control my operating system. It allows me to load applications. It allows me to change some things inside my computer. It allows different functions. It has some built-in applications, like this guy right here that allows me to look at my folder. That's a built-in application that's in the operating system. But the shell allows you to do that. So the operating system, that's the machine code program that runs the computer. This is machine code. An application program, we refer to those as apps. A driver, I don't know, a driver is a machine, that's a machine program that controls a certain device. So you have a driver for your display, you have a driver for your keyboard, you have a driver for your hard drive, you have a driver for your USB ports. All those are part of the operating system. If you stick a USB port in there that doesn't have, if you stick a USB device in there that doesn't have your operating system doesn't have that driver, a little gray box will pop up out there saying, loading software or loading driver. And what you're doing is you can add up multiple drivers to your operating system. I don't know why that's not all over here. We looked at a compiler. A compiler is a machine language program that translates a high-level language program into a standalone machine language program. So both our RSLogic 500 runs a compiler. So when we download it to our PLC, and that's going to be backwards, guys, from what you learned from upload and download. A download means you're sending the program to the PLC. It's going to be compiled when it's sent over there. So the PLC does never ever see a high-level language program. Interpreters, these are going to be simulators. So we're going to look at a simulator called Logic Pro. Which you can buy. A permanent license is like $45, but it's simulated. So you don't have real inputs, you don't have real outputs. You're going to have pictures that display those. But you could learn a lot about programming those, and you can download a lab book where it's got a program where you can write to control elevators. You can write one to control a garage door opener, which is pretty cool. But it's interpreted. RSLogic 5000 has a simulator that you can actually load, and it's going to be interpreted. It's not going to be compiled. Let's see. Allen Bradley automated controller, personal PC. This right here we don't need to know. Let's see. So basically, when we buy PLCs. How many inputs what processor does it have? What speed does it have? What memory we have? If you buy a modular PLC, what modules are available for it? How many inputs can we put? How many outputs can we put? What do we have communication modules available where we can take one method of communicating and convert it over to another? So that would all be what you would look at. Fixed PLCs, though, you got to remember, once you buy them, you got the processor, you got the speed, you got the memory, and you got the input-outputs, and you can't add anything, you can't expand them at all. So the big advantage of a modular PLC is that we can expand them. The big advantages of a fixed PLC is cheap. So. But you get what you pay for, and a lot of times that's all you need, So that's it.